I've completed my round to nearest even for my 32-bit floating point adder and subtractor. Now I will be going through the details of this in the full course, but let's just talk through and I'll show you roughly the changes I've had to make in order to get this to work. So you can see here that we've got the shifter here and we've got the sticky bit. Now previously within the shifter, if I was to say for example I had a number here 1011 for our MY, then in order to do the alignment properly I would have to do the shift here. So the EX minus EY, let's say for example it was a value of 1, then I would have to shift this here to the right by a value of 1. Now previously what would happen is that we would just do the shift and we would get this value here 101, and this 1 would be shifted off the end and it would just be lost. Now what we want to do in order to do the rounding is we want to take a copy of any bits that get shifted over to the right, because those bits will be used in order to provide our rounding. So the circuit that was a bit awkward was this little circuit here. Now you can see here that I've now got a copy of this 1 bit here, so that's 1 bit and the other bits here are just zeros. Now if I was to shift this off by a value of 2, you can see here we're going to have the first 2 bits here, so it'll become 1, 1. So we save these 2 bits here. Now if I had a value of say 3, then it would be 0, 1, 1, and if it was a value of say for example 4, then we'd be shifting this 1, 0, 1, 1, and it gets shifted off the end here and it becomes 1, 0, 1, 1. So these are the bits here we're going to use for our rounding. The first bit is going to be our guard bit, and you can see I've got a copy of the guard bit here as an output. Now the other 23 bits here are going to be ORed together. So these are our sticky bits, and what we're going to do is we OR them all together, and the ORing of these just gives us a round bit. Okay, now again I'll talk through this in detail whenever I get through the course, because it gets quite confusing. There's the sticky bits, round bits, guard bits, and the IEEE 754 standard doesn't actually mention these bits, it just mentions rounding mechanisms. Okay, so how you interpret these bits really is different depending on exactly how you're implementing it, but we'll talk about that again whenever I go through the details of the course. So we have the output here, okay, and you can see here that we've got our guard bit and we've got our sticky bit, which becomes the round bit. Now there's another complication, that is that we also have to take care of the fact that there might be a normalization. So if there is a normalization, it means that we're going to have to then shift the values here by either a factor of 1, either left or right. So if for example we have a subtraction and it creates a cancellation, it would mean that we're going to end up with the mantissa multiplied by 2, so that is, it's going to be shifted to the left. So if it's shifted to the left by a value of 1, it means that this entire value here gets shifted to the left by a factor of 1. So it means that this bit here, now that we've saved, which was the guard bit, now gets shifted up and becomes the least significant bit. Okay, so that's part of the reason why we want to save this, because we want to retain that information. So that we have to take care of that elsewhere in the circuit, but this is a little note of it here. Now the other option here is that if we had an addition and if there's a ripple through into the exponent, we also have the mantissa would be a division by 2, that is, it would be shifted to the right. Now if it shifts to the right, again it means we've got an extra shift here. Okay, so in effect we would be shifting this another 1. Okay, and it would mean that the guard bit would potentially change. Okay, so you see in this instance here the guard bit is in fact changing. So we would have to have a note of whether we are subtracting with a cancellation or whether we're adding with a ripple carry, or the option where there's just no change, and these values here come from the normalization block. Again, I don't expect you to pick this up from this video, but it's just an indication of how things are working and how much detail I had to get into to get this working. So you can see the normalization, and the normalization unit here, the outputs get fed back up into the shifter to create our guard bit and our round bit. So if we go down in here, you can see we've added this extra section in here, and the choice of whether we add with ripple or we subtract with a cancellation, or whether there's no change, is dependent on a little truth table. Now, I don't have the truth table written down here, but I will provide it whenever I create the course. So the little truth table will be dependent on whether it's an addition or a subtraction, that's the plus minus, and also the value for the 24th and the 25th bit whenever we do the addition. And that's the Boolean realization of this little truth table that I've mentioned. So once we've got this information and it's in the right format, we've now got the round bit for the far side, we've got the guard bit for the far side here. Then we can choose this along with the output from the far side, or if we were to go to the near side, and the near side's a bit simpler, we don't have any rounding for the near side, or the rounding is minimal, because if we have the near side as the exponent difference is a value of 0, if there's 0 exponent difference, then there isn't any shift. So if we aren't shifting, we aren't moving any values out into the rounding section, so there is no rounding, the values are exact. The only other option is that we actually have a shift of a value of 1, but we've taken care of that shift of a value of 1 within here, and again I'll go over in the course. So finally, whenever we have our output here, we are going to either choose this lot of results here, or this lot of results here, in which case we're going to have to go through the rounding. So the rounding is the same tie to nearest even rounding that we used for the multiplication, and this is the truth table for it here, and this is the Boolean realization of this little truth table. We also have a few, well, one extra little added complication, and that is the least significant bit, because we mentioned before, if we have a cancellation, then we're going to have to shift to the left by 1, in which case the guard bit becomes the least significant bit. So it means that the least significant bit has to be chosen properly, and we have to actually choose the guard bit for that in that instance. So that's the only extra little bit of complication, and it took me a little bit of a while to work that one out. But that's the circuit here, and you can see we inject the round bit here, and we have a potential of injecting the round bit all the way up through the mantissa, all the way up through the exponent, and there's a chance, of course, that the value will actually overflow. So we've got an overflow here, but we'll talk about that, we'll go through that in detail in a different video. So that's ostensibly the changes that I've had to make in order to put in the round to nearest even, and I have tested it out in a few values and it does seem to work okay. So that's all for this video. Tomorrow I will go on and I will add in the subnormal numbers, and you can see I've actually already started doing that. I have a splitter up here, and I've got the test to find out whether the x value is a normal or subnormal, and the y value is a normal or subnormal. So that's a start on that, and as I say, tomorrow I'll hopefully take a day or so to implement that, and then another day or so to implement the special values like plus and minus infinity, not a number, all the overflows and the underflows. So possibly 2 or 3 days to get the whole thing finished, and then the course, I'll start producing the proper videos for the course, and the proper videos for the course should only be maybe 10 minutes long for each, so I'm trying to keep it at a maximum of 10 minutes for each of them. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.